Good morning, students. Welcome back to Laser Technologies course. So in the last class, we have discussed about the course contents and fundamentals of lasers, optical absorption. So in the optical absorption, we have discussed a few basics, and now you continue with that. Here I have considered two energy levels, E1 and E2, of a material system. So the material with the length L I have shown here. What are the possibilities that electron or atom go to excited state? So right now the electron in the ground state, how it can go to excited state? Yes, it has two possibilities. Either the electron can absorb a photon, or with a collision with the other atoms or nearby atoms or particles, it can go to excited state. So to go to excited state, the photon which is interacting with the material system or with these two energy levels, it has to be equal to the difference of the E2 minus E1. E2 minus E1 is nothing but energy gap. When the photon interacts with the electron in the ground state, the energy of the photon is transferred to electron and go to excited state. So that this is a microscopic picture. In the macroscopic picture, in the material system, the light beam has a stream of photon. When it interacts with the material, there is large number of photons will get absorbed in the material medium. The portion of the light will the amount of the light which come out from the material will reduces. That is why you see the fainted beam coming from the material. So where I input is input intensity of the light, where I naught is the output intensity of the light after passing through a material. So your output intensity is proportional to your input intensity, and also is depending upon the length of the material and internal property of the material. So your I naught is nothing but I input and exponential e power minus alpha L. So if you plot I versus length L, you can see the intensity is decreases as length is increases. So as length of the intensity increases, the output intensity is decreases, because as length increases, more number of electrons will be excited to excited state. So the energy of the photons will lose. In that case, the output intensity will be less. So your I naught equals to I input in e power minus alpha L. So this alpha is inherent property of the material. From this equation, you can calculate the transmission. The transmission is nothing but output intensity by input intensity. That is nothing but e power minus alpha L. From this, you can calculate 1 hour transmission. So if you take logarithm on both sides, you will get log E 1 over T equals to alpha L. Your alpha equals to 1 hour length log of 1 hour transmission. So this is called absorption coefficient. See, this absorption coefficient of a material is constant. For a given material, it is a constant, and for the different materials, this alpha will changes depending upon the material inherent property. How the photons interact with the electrons and how many number of electrons are excited, that depends your absorption coefficient. Or so your transmission percentage is equals to I naught by I input into 100. From this absorption coefficient, if you know absorption coefficient of any given any material for any given length, you can find out what is the absorption percentage and what is the transmission percentage. So that is the advantage of this absorption coefficient. So now we move on to spontaneous emission. Here I consider two energy level system. So where the electron is already in the excited state. Now what are the possibilities that it can come back to ground state? So if it come back to ground state spontaneously, that means without any external triggering, without applying any force or without applying any energy, it will automatically come down and it releases its excess energy either as a photon or a heat. See, the typical excited state lifetime is the order of 10 to minus 8 seconds. That is the average lifetime. And if you consider many number of electrons in the excited state, they come to ground state at different time scales, as you see in this figure. Now, this decay back to ground state happens at different time scales. Because of these different time scales, you can see it acquires, the emitted photon acquires different phases, and this is all random process and it emits in all directions. So that is why your spontaneous emission of light is incoherent light. If the electron in the excited state, there is another possibility that you can trigger this electron to move to ground state by external force, like applying a photon. This photon interacts with the excited atom, then it emits another photon with the same frequency and the same phase and same direction with the triggered photon. So this process is called stimulated emission. So now if you see two photons incident on the two excited atoms system, then you are able to get 4 photons as output. So, but all the photons will decay to, all the electrons will decay to ground state at the same time. That's the reason it acquires the same phase and also it follows the direction of the triggered photon. That gives you a unidirectional beam, and the process, the immediate emission of light, is coherent. So that is the reason your laser beam is always unidirectional. Okay, so now we are going to discuss about Einstein coefficients. So all these phenomena is modeled by Einstein in 1915. So in this case, I consider two energy levels E1 and E2. So N1 and N2 are the number of atoms or electrons in the excited state and the ground state. So N2 are the atoms in the excited state and N1 is number of atoms in the ground state. So now, if the radiation frequency corresponding to E2 minus E1 falls on the material system, it can interact with 3 different ways. One is stimulated absorption, spontaneous emission, and stimulated emission. The stimulated absorption. So now, if the external photon is triggering to make the electron in the ground state to take a transition to excited state E2, this process is called a stimulated absorption. So the total rate at which absorption takes place from energy level E1 to E2 is proportional to number of the atoms in the energy level E1 and also the energy density of the radiation at the frequency omega, that is nothing but E2 minus E1 by h cross. U of omega d omega represents the radiation energy for unit volume between omega and omega plus d omega. Omega plus d omega. The number of atoms undergoing absorption per unit time and unit volume from energy level 1 to 2, that is nothing but the rate of change of number of atoms in the ground state is proportional to u of omega and n1. So u of omega is your energy density and n1 is the number of atoms in the ground state. So if you remove the proportionality, then you have introduce a proportional constant, that is V12, and u of omega is energy density per frequency interval. So this equation 1 is represents the rate of the change of the atoms in the ground state. In come to spontaneous emission, so there is number of atoms in the excited state E2. They will come back to ground state spontaneously and emit the radiation. The rate at which emission takes place from energy level E2 to E1 is proportional to number of atoms in level E2. So we can calculate the number of atoms undergoing emission for unit time and unit volume from energy level E2 to E1 is nothing but dN2 by dt proportional to number of atoms in the N2 excited state E2. So that is nothing but you remove the proportionality constant, your dN2 by dt equals to minus A21 N2. Where A21 is the proportionality constant, and now the stimulated emission. So now we come with the external triggering, that is photon is interacting with the atoms in the excited state E2, the number of atoms in the excited state E2. So the rate at which emission takes place from energy level E2 to E1 is proportional to number of atoms in the level E2 and also the energy density of the radiation at frequency omega, that equals to E2 minus E1 by h cross. The number of atoms undergoing stimulated emission per unit time and unit volume from energy level 2 to energy level 1. So that is nothing but dN2 by dt, the rate of change of the atoms in the excited state E2 is proportional to the incident energy density of the radiation and the number of atoms in the excited state N2. So if you remove the proportionality constant, you get the minus BT1. So where minus is a convention, because the transition is happening from E2 to E1, so you will take the minus signature. So your V21 is the proportionality constant. Okay. So now in the excited state, so in the real picture, what is meant by excitation or excited state? So now if you see here in this figure 1, the simple pendulum of mass m is hanging at a fixed position. If you apply a small force or energy, give it a small energy, it will oscillate from its mean position. Okay, it oscillates from its mean position. Then now that means the system in the excited state. How long it can be there? It cannot be forever. It has to come back to mean position. That is your, that's a stable position or equilibrium state. Okay, and similarly, you can consider the molecular level. You have a hydrogen atom, H2O. You consider H2O. So now if you see your oxygen and hydrogen are connected, now this oxygen, if you give a small energy, this oxygen will stretch for a certain time. Okay, so that is the excited state of this atom, or this will rotate. If you give a small energy, it will rotate. It rotates for a certain time. The time is because of the lifetime of this state. Like in this case, in the simple pendulum, it has a certain lifetime to come back to ground state. for a stable state. Similarly, it happens in the molecule system. After a certain time scale of the rotation, it go back to its ground state. So this is your real picture representation of the excited state. Okay. In the next class, we discuss what Einstein coefficient further.